Hi Jardel. Okay, so let's get straight into it. So pretty much what I've done is I've answered the question on this piece of paper. Oh, I don't know if you'll be able to see it. I don't know whether it's going to show back to front for you watching this, or I think it might. So what I'm going to do is I'm just going to read out what I've done on the piece of paper, and I'm also going to send you an image of this, and you'll be able to sort of follow it along as I read it out. Okay, so up the top, ignore the E equals thing. I've written F equals, and then you've got like a weird sort of fraction there. It says 1 over 4 pi and then like an E naught thing. Don't worry too much about this. This is just Coulomb's constant, which is also represented by the letter K, which is 9 times 10 to the power of 9. That's all you need to know. It's constant, obviously it never changes, and you just use it every time you're calculating the electric force, and consequently you'll use it when you're calculating the electric field, because obviously electric field is force over the charge. So just remember 9 times 10 to the power of 9. You'll see I accidentally did a -9 up there, and then I scribbled it out. So just make sure it's 9 times 10 to the 9. And Q1 and Q2 are obviously the values of the charges. And you generally get those in microcoulombs. You might get them in normal coulombs. The question has given us microcoulombs, but I've walked you through how to convert those. And your R is just the distance between the two charges. Pretty simple. Alright, so let's have a look at our charges. So we've got Q1, Q2 and Q3, and there's our little diagram showing how far apart they are. We've got Q3 in the middle and Q1 and Q2 on opposite ends, and Q1 and Q2 are exactly 0.2 meters apart, or 20 centimeters. Always convert into meters first, and Q3 lies in the middle of that. So obviously the distance between Q1 and Q3 is going to be 0.1 meters or 10 centimeters, and the distance between Q2 and Q3 is also going to be 10 centimeters or 0.1 meters. So that's well, we've got our charges. We've got Q1, which is 5 microcoulombs. Now, if you want, you can really just get a calculator, slap it in here. If I do 5 times 10 to the power of -6, oh, that's what I forgot to mention. Micro means times 10 to the -6. So if I say a microcoulomb, 1 microcoulomb is 1 times 10 to the power of -6, okay? So if it says 5 microcoulombs, it's 5 times 10 to the -6. Here for Q2, we've got 50 microcoulombs, which is going to be 50 times 10 to the -6, but because we want to change it into like a single, I think it's standard notation, scientific notation, I'm not sure what it's called. We want to make sure that it's only a single number times 10 to the power of whatever. So 50 microcoulombs is actually 5 times 10 to the -5, because obviously 50 is larger, and 10 to the -6 is going to have another 0 on the end than to the -5, if that makes sense. So I'll just in case, I'll just draw it out here. So I'll do 1 times 10 to the -6. You can see it has that many zeros, and now I'll just do 1 times 10 to the -3, for example, to show you. Obviously it's going to be a lot bigger than 1 times 10 to the -6. So we're going to change 50 microcoulombs to 5 times 10 to the -5, because we've got that extra 0 there. We can add on one of the extra decimal places. Then Q3, exactly the same thing as Q2. We've got 30 microcoulombs. We're going to change it to 3 times 10 to the -5. Alright, so now we've got part A. Now part A says, okay, so it says find the force on Q3 if Q1 and Q2 are both positive. Okay, so already we know like charges repel. So we know that everything is going to repel away from each other here. We've just got to find out ultimately what the magnitude of that resultant force is and what direction it's in, because obviously, I mean, if all of the point charges were the same, then theoretically there would be no net force, but there is going to be a net force because we've got 3 different magnitudes of charges. And if you have a look at the equation for force here, you can see that the force is directly proportional to the charges. And so what that means is that the bigger the charges, the bigger the force. Alright, so let's start with part A. So Q1 and Q2 are both positive, and so for the, I want you to have a look at the, sorry, someone just did a whistle or something. Anyway, if you have a look at the picture of this that I've sent you. You can follow this while I'm reading it along now. So force 1, I've labelled it, is of Q1 onto Q3, and I've done coulombs constant, which is 9 times 10 to the 9, times by 5 times 10 to the negative 6, which is that's our Q1, and then 3 times 10 to the negative 5, which is our Q3. Then I've done that over 0.1 squared. Obviously that's our radius, and we have to do a radius squared for our force. Now, what our answer was 135 newtons, and that's going to be in opposite directions. You can also say the repulsive force or whatever, because it's between two positive charges, whatever. You can say what you want. Generally with direction, as long as you put something, examiners aren't going to be too harsh with direction. Maybe check that with your teacher, but in my experience, as long as you provided something, just with charges, because you're not given anything like east and west unless you start using vectors, start doing, like, you might have a charge here, and a charge here. That's when you have to start giving direction. But when you've just got a linear sort of problem like this, it's not really a big deal. Anyway, so then we've got the second force, which is Q2 on Q3, and so I've just, you can see what numbers I've subbed in there. I've just put the coulombs constant, and then I've put Q2, and then I've put Q3, and then I've done that over R squared. And then we've got 1,350 newtons. Obviously, again, they're in the repulsive direction because they're exerting force on each other. Now, our net force, which is ultimately what the question is asking, is going to be 1,350 newtons subtract 135, and I'll show you why. Let me actually see if I can draw a little bit of a diagram just quickly. I have written here, it's 1,215 newtons towards Q1, and that's because the force of Q2 on Q3 is greater. Now, let me get a piece of paper out. Now, we've got Q3 in the middle, Q2 on the sides, and Q1 on the side. Now, 1,350 newtons. 135 newtons. Now you can see here that actually, you know, I'll make it look bigger. Like I'll do like a big arrow. Okay, so this force here, 1,350 newtons, is obviously a lot bigger than this force here, which is just 135 newtons. So Q2 is going to push Q3 closer towards Q1 because that force, that repulsive force, is going to be greater, right? Oop, dropped the sheet. Anyway, so that's how you answer question 1 part A. And part B is when we change Q2 to negative. Now, obviously, you know, like charges repel and opposite charges attract. So that means that we're going to have to work out now, what does this mean for the net force? Because obviously our magnitudes are going to stay relatively similar. Obviously our net force is going to be different, but our magnitudes of F1 and F2 are going to be exactly the same. So if you just follow along on the sheet, I've got F1 equals 135 newtons in the opposite direction, or whatever, you know, repulsive force, and that's because Q3 and Q1 are still going to be positive. Now Q2 has changed to negative, so we can say F2 is 1,350 newtons towards each other in the same direction, attractive force, whatever you want, okay? Now our net force is going to look a little bit more like this. All right, I'm just going to get my little piece of paper again and draw it out. So we've got Q3, Q2, Q1. Okay, so now Q3 is being pulled towards Q2, and Q1 is still, 135 newtons. So, oh, is it gonna work? Yeah, Q3, did I write that right? Yeah, Q3 is being pulled towards Q2 because there's an attractive force. This is negative, this is positive, but Q1 is pushing it away. So can you see that the net force is going to be in this direction? So instead of subtracting, because those are going the opposite directions, we're going to add them up together because it's going to increase the magnitude, right? It's going to sort of like build up on itself. So what we've just done is 1,350 plus 135 equals 1,485 newtons towards Q2, obviously, because that's the direction that Q1 is pushing it in and Q3 is attracted to it. So that's all that you need to know for that question. I hope I did that right. I honestly did it in about 3 minutes because I'm about to head off to a lecture. Let me know if you've got any other questions. If you can send me these questions, they're really, really good. Otherwise, I don't actually have any of my physics book with me, so it's hard for me to go through the theory until I see you next. Send me as many questions as you can and I'll do my best to get to them, but I'm coming up to exam period soon, so it might be a bit busy for me as well. I'll try and keep you as updated as I can with everything though. Yeah, good luck with everything if I don't chat to you before then. Bye.